All right, good morning. We still got about 2 minutes of morning time. Well, since I'm here already, if anyone has any questions, now we can use this time to kind of ask questions and I can answer those. All right, maybe not. So as a quick outline of what we're gonna do today, the first part is to kind of revisit exam 1. So I'm gonna go through my own, test, just to kind of talk about, what I'm expecting in the answer, especially the last two. But interestingly, I think more questions were asked about the first 5 questions. So we'll definitely get that done first. And then we're going to move on to finish up the relation topic. And if we still have time left, we'll move on to propositional logic. So that's kind of the plan for today. All right, so I'm still not seeing any messages from the text channel. Just want to make sure that I did not leave things turned off from last Wednesday. Okay, well, one of you can try to. Oh, okay, there we go. I can see it. Yep. I'm just not sure whether people don't have questions or whether I forgot to turn it back on. I checked. I turned everything back on, but sometimes I forget a few really crucial things and then it doesn't work. All right, so it is time. I'm gonna get started with the exam. So exam 1 has I would say a lot of resemblance with the practice test, yes, but some people may disagree. So the first 5 questions, they all have the same format. The first thing is I explain that the left arrow is an assignment operator, which is really just copying whatever the right hand side is to the left hand side. So whatever y has as a value, now x has it. So that's kind of the idea of an assignment, which is used later on because I want to basically clone the values of x, y, and f in each one of the questions. Okay, so in this case, you are given that x as a set has 0, 1, 2, 3, y also has 1, 0, 1, 2, 3, and then f is a set of 2 tuples, which would be 0, 2 as 1, 1, 1 as 1, 2, 0 as 1, 3, 0 as another one. So now we can sort of move on to the individual parts. So we go to part 1 first in this case. So all the questions from 1 to 4, okay, I take it back, it's only 1, 2, 3. So from 1 to 3 as a part of each question, it will tell you that you are supposed to clone f, x, and y into f0, f1, f2, and so on, with the x and also with the y. And I want you to make minimal changes to f0, x0, and or y0. So you can make changes to all 3 sets in order to make f0 an injection but not a surjection in this case. So starting off with these given values, how can you make f0 into an injection but not a surjection, but we want it to be as close to the original f as possible. So we want to make the minimum number of changes. So with this, I can use the tablet, but I think it's easier to use just a text editor, because it's just writing set notations. So let's go ahead and find out what we can do in this case. So we want this to be an injection, but not a surjection. We want to so we look at the original f, and then we ask how can we make f0 to make that happen. So to make this an injection, it is not an injection at this point, because we can see even though it is a function, f itself is already a function, but it is not an injection because both 2 and 3 map to 0. So we basically have to add one more item in order to add one more item to the codomain that is not mapped to, that will make it not a surjection. So one way to do this, now this is not by any means the only way to do it, because out of 2, 0 and 3, 0, you can pick whichever one you want to map to a different element. So I'm just going to change what 3 maps to. So 3 maps to 3. So f0 would look like this. I don't want to change x, okay? The set of all the domain doesn't need to change, but the codomain needs to change, because I need to make the codomain 0, 1, 2, 3, and then add a 4 to it, because this way the element 4 is not mapped to, and as a result, this f0 is a function mapping from x0, which is just x, to y0, and it is an injection because every element in the domain maps to a unique element in the codomain, but at the same time it is not a surjection. Alright, so we got some questions coming in, which is good. Okay, so as the questions are coming in, I can start on the next one. So the next one says, we want f1 to be a surjection but not an injection. So so your question will be different, okay? Including which part ask about an injection but not a surjection, which part ask about a surjection but not an injection, and which part ask about a bijection. All of those are scrambled, depending on which question you're getting, and that's intentional. I mean, just to move things around a little bit. All right, so I'm gonna wait for the question. All right, so the question is, if I want to minimize the size of the union, I can get rid of 3, 0 in f0 and get rid of 3 in x0. That is true, but we also want to maximize the intersection at the same time. But I think Jonathan has a better solution in this case, because the union will be smaller, but because we are retaining most of the elements in f0, because we're keeping basically all except for the last one. So that would actually be a better solution. Jonathan's solution Jack's solution is actually better. So let me just kind of echo what Jack's solution is. So Jack's solution is to say, let's make f0 0, 2. So we are keeping the first 3 elements because those 3 would make every element in the domain map to a unique element in the codomain, but then 3 is not mapped. So instead of making changes to y, we are now making changes to x. So x would only have 0, 1, 2 in it, and this would also meet all the requirements, but it would do a better job in order to minimize the union of all of the f's, while at the same time maximizing the intersection of all the f's. So yes, so Jack's solution is actually better. Very good. So now we move on to part 2. So part 2 wants about the same thing, except this time we want it to be not an injection but a surjection. So that means, let me see which would. There are many ways to do it. The question is, what is the best way to doing it? The original set is already Oh, this would be easy, right? Because we can keep f, and then all we have to do is to remove 3 as an element from y, and we're done. Alright, so in this case, f1 is going to be the same as f, which means you don't have to mention anything because we're keeping it the same. But what we're going to change is just y. So y1 is the one that is being changed. It would only contain 0, 1, and 2. So that will make f1 as a function mapping from x1, which is the same as x, to y1, which is kind of the same as y, but without the element 3. This will meet all the requirements. And because we are not making changes to f, so we are also not going to reduce the intersection any further. So that would be a solution for f1. And then f2 wants to be a bijection. So this time we want both injection and surjection, and I intentionally did not define what is a bijection in the question itself, because I think that's legitimately something that I should ask, so that people understand bijection is really just injection and surjection. So in this case, f2 is going to be I want to maintain as much as possible, so I want to keep the same first 3 elements, and then for the 4th element, I'm gonna map 3 to 3, for instance. So gonna use that here, and then for x and y, we don't have to make any changes. So in this case, f2 is the only one that needs to be changed for answer part 3, because we just have to change 3 to map to 3, or you can change 2 to map to 3. I mean, just pick one of these 2 to map to 3 and use up all of the elements. But since I have preserved 2, 0 in the previous 2 questions, so it makes more sense to preserve 2, 0 here as well, and instead I just change 3, 3 to wherever it needs to go. So with all of these, now we look at the intersection. Okay, so intersection of f, f0, f1, and f2. So that would be the elements that are common to all 4 sets in this case. So that's going to be 0, 2, 1, 1, and 2, 0. So those are the ones that are preserved. They're common in every single one of those sets. And then when we look at the union, that means we are looking at elements that is in at least one of the 4 f's, right? So we got 0, 2. Okay, so the entire intersection has to be here. Okay, and then we also have to account for things that may be in just one of the 4 f's, and that would be 3, 3. So if you look at this, there are 2 ways to answer the first part. Either way is okay, because we have 3, 3 already introduced in the 3rd part of the question. So either way is fine, because we are not there's no goal set to either minimize or maximize x and y. So that's so Jack's solution is okay, but my original solution is okay as well. They give us the same optimized intersection and the same optimized union of all the f's. Alright, so that answers part 4 and part 5, and then part 6 wants to ask what is f1 minus f. So f1 minus f, so f1 minus f would be elements that are in f but not in f1. Let me see. No, the other way around. In f1 but not in f. There we go. So we look at f1, and f1 is the same as f, so the subtraction would be an empty set. There's nothing in f1 that is not in f. That's basically what this is saying. And then part 7 is a quantified expression, and I'm looking for the value of the expression and also an explanation of why that is the case. So let's take a look at the quantified expression first. And there were a few questions in class, during the exam, where A and B are coming from. That's something that we talked about in quantified expressions. Those are your quantified variables, because otherwise I can't, refer to things, in the inequality. So there exists a in f0 simply means, there's at least one element that we can choose for variable a in f0, and so that, no matter what b you choose from f1, the following is remaining true. Okay, a does not equal to b. So what it really is asking is, can we find at least one thing in f0 that is not in f1? Okay, so we're looking for something, at least one thing that is in f0 but not in f1. So, depending on which answer you're picking, okay, so this time it depends on whether you're using Jack's solution. Jack's solution in this case would, let's see. So in Jack's case, it would give us, the answer would be false because there's nothing in f0 that is not in f1. In using my solution, it's going to be the same because f1 is the same as f. So to answer that particular question, the last part, the answer is false. There is no element in f0 that is different from all elements of f1. So that would be kind of my way of explaining it. You don't have to use exactly the same word, but the idea has to be there. All right. So are there any questions about question number 1 of 7? I'm just looking at the text channel. Doesn't seem to have any questions. All right. So I'm going to assume that we are okay with question number 1. Does anyone want to go over any one of the first 5 questions? Because they are all about the same. It's just that the initial f is different. Some would start with an f that is not a function because it has too many items. And some would start with an f that has 2 little items like this one over here. And no, don't worry. Everybody would get the same combination of scenarios. So no one is going to get all the easy ones. Oh, finally, we got a question coming. We got 2 questions coming. Very good. Alright, so Yolanda's question is, will we be able to see the exam with my feedback? That is a good question. Depends on... I'll see what I can do. I will see what I can do. I suppose we can go over all the questions but at the same time they're very, very similar. Okay, so we can do that. Okay, all right. So let's go ahead and continue with solving question number 2 then. So with question number 2, we want the first part 1 is now asking how to make it into a bijection, and it starts off with something like this, which is not even a function to begin with. Alright, so if it is not a function to begin with, we have to kind of think about, why is it not a function, and how do we make it into a function, and make it into a function that is also a bijection. So if we want to turn it into a bijection, unless you want to remove more elements than you need to, which is okay, because, just like what Jack said, that's one way to make things happen. The other thing is to keep x and y the same, and then just make changes to f itself. Alright, so I thought there were a few, I thought Li Yu was asking something, but the question did not pop up, in the text channel, so I'm gonna keep going here. Okay, so if we keep 0, 1, 1, 3, 2, 0, and 3, 2, That would give us a bijection already. So that would be the easiest thing to do is to remove the element 1, 1 from the set. Okay, so Liu said, I think my question is costing too much time to figure out what the question is asking me. Is that a comment? Is it a opinion, or is this actually a question? Because it is not in the form of a question. Alex Trebek would not have accepted this in the game show. So I'm still not clear what Liu is referring to, whether it's a question or a comment. But we'll go ahead and continue with this question. So until there's a clarification. Yes, he would be. He's a terrific game show host, but also as a person too. So kind of cool guy. All right, so F0 is going to be 0, 1, 1, 3, 2, 0, and then 3, 2. Okay, because now it is a bijection. I don't even need to make any changes to x or y in this case. Moving on to part 2. So F1, to answer part 2, is we want it to be a surjection but not an injection. So we want everything in the codomain to be used. Yes, we want everything in the codomain to be used, but we don't necessarily map everything to unique elements. We don't necessarily map every element in the domain to unique items in the codomain. Alright, so let's see what is the easiest or the laziest way to make changes to F to make this happen. Alright, so I think I got one. We keep 0, 1, we keep 1, 1 in this case, we keep 2, 0, and then we keep 3, 2. That's for F1, but we also need to make some changes because we want to make this a surjection. So with this, 3 is not mapped to, so we want y1 not to have 3. So y1 would only have 0, 1, and 2 in it, and 3 is not a part of y1. Moving on to part 3. So in part 3, we want it to be an injection but not a surjection. So we want everything to map to unique items, but we want to leave certain things that are unmapped in the codomain. So the easiest way to do this is to make it the same as F0. So we'll make F2 the same as F0. And this is the one thing that you can do in the test is you can copy and paste as long as it is clear that you're copying and pasting from your own document. That's perfectly okay. Okay, and in this case, it's really clear that we are copying from the same document because we just had that written a little bit earlier. So in order to make this not a surjection, we just have to make the the codomain a little bit bigger. So we now say F1 is 0, 1, 2, 3, 4. We just introduce an extra element in y2, and we're done. There we go. Now we need to do the intersection of all the f's. Okay, so I'm just going to say intersection here, understood that this is the intersection of f, f0, f1, and f2. So the intersection is going to be just everything that is common to all of these sets need to be put here. So 0, 1 appears in all. 1, 3 does not appear in all. 2, 0 appears in all, and then 3, 2 also appears in all. So it will be these 3 in the intersection, and then the union would be the elements that appear in at least one of the 4 sets, right? So it will be 0, 1, 1, 3, 1, 1, because 1, 1 was found in both F1 and the original F, and then we got 2, 0, and then 3, 2 in this case. And this is pretty much as small as as small of a unit as you can get, because this is the entire F to begin with. So there's no way to make the union any smaller than this. All right. Okay. I don't know what to say about that. I try my best to make the questions as easy to understand as possible. So um, unless someone can give me a concrete example of how to phrase the question differently, I understand. It may be difficult for some people to understand the question itself, but I would not know how to rephrase the question unless somebody says, "Oh, but you could have phrased this in this particular way." All right. So question number 3. So question number 3 starts with also a let's see, is this a function? Nope, this is not a function because 2 maps to 1 and 2 maps to 3 also. So this is also not a function to begin with. F is not a function. But that's okay. I'm not even asking whether f is a function or not. I just want to use f as the starting point and then make f0, f1, f2 into functions with special properties. So let's go ahead and get started with this one. I mean, when you guys are bored with this, we can skip some of the questions of the same format. Okay, but until then, we can go ahead and keep doing it. All right, so part 1 is asking we want it to be a bijection. Okay, so if you want this to be a bijection, let's see, we have to make 2 changes, right? Let's see, so we can keep these 2 and then we can keep this one, and then we have to change this one here. So that's all we need to do is to change that one to, so the 2 maps to 2. Okay, so that's the way to fix it. So f0 is going to be a set that has 0, 1, 1, 0, 2, 2, and then 2, 3. Oh, I guess not, because we need this and this thing to be entirely different. So it needs to be 3, 2, and then we keep 2, 3 in the set. So this will make it a bijection because we can see that at least it is a function, because we can see 0, 1, 2, 3 are all in it and only appearing once. So we have each element in the domain mapping to one and only one element in the codomain. We also can see that we have 0, 1, 2, 3. Okay, so that means each element in the domain is mapped to a unique element in the codomain. And because the x and y starts off with just 0, 1, 2, and 3, we can see that we are using everything in the codomain. So this basically solves the problem that we need to do. Okay, for the first part. The second part wants it to be an injection but not a surjection. I think at this point you guys already know, what is the standard answer to make that happen. There are several ways to do it, but there's no super easy way to do that. Because in the original set, one of the 2 needs to be changed. So in this case, oh, okay, I can see how we can make f1 a smaller set. Okay, so we keep 0, 1, we keep 1, 0, and then we keep 2, 3 as our f1. And the question is, we want it to be an injection but not a surjection. So in this case, we also have to change x, which is the set of all the domain, because in this case the x1 can only have 0, 1, and 2 in it, because 3 is not mapped to anything. So if x1 includes 3, then f1 would not have been a function. So we have to take the element 3 out of x1 in order for this particular f1 to be a function. But y1 we want to keep the same because we don't want it to be a surjection. So that means it's okay to have 2 as the extra element in y1 that is not mapped to. All right, so now we move on to question number 3. We want a surjection but not an injection. All right, so let's see what is the quickest and easiest way to make that happen. All right, so we want it to be a surjection but not an injection. So we have 0, 1, 1, 0. We keep both of those. And then since we have 2, 3 already used in F0 and F1, we want to keep that one too. So that means we can introduce a 3, 3 into it. Then we can change Y so that it is a surjection, but it won't be injection because we are mapping 2 and 3 both to 3. Okay, so let me write it out. So we got 0, 1, we got 1, 0, we got 2 mapped to 3, and then we got 3 mapped to 3, and then we got 2 mapped to 3 as well. So, but we also need to make one change. Let me see. We want it to be a surjection, but not an injection. Okay, so we do need to make one change to Y. So the Y2 cannot have the element 2 in it. So 0, 1, 3 are the only 3 elements we want to keep in Y2, because otherwise it would not have been a surjection. A surjection means all the elements in the codomain are mapped to. So in this case we have 1, 0, 3 mapped to already. 3 is mapped to twice, which is the whole point of making this not an injection. Alright, so now we look at the intersection. So as far as the intersection is concerned, it is the same as F1. So the intersection is 0, 1, 1, 0, and 2, 3. And then when we look at the union is going to have 0, 1, 1, 0. It's going to have 3, 3. It's going to have 2, 3. And there's also a 3, 2 in it. Makes me wonder whether there's a way to make it smaller, but as it is right now, this is the union. Alright, and then we look at F1 minus F. So F1 minus F would be, this is F1, and let's see what F looks like. F looks like this, right? Okay, so F1 has everything in F1 is in F, so this would be an empty set. And then we have to evaluate the quantified expression, which is asking, is there at least one thing in F0 that everything in F1 are different to? So we now look at F0, and then we look at F1, and we can say, yep, we can definitely find that 3, 2 is there. Okay, so we can basically now, for part 7, the answer is true, because 3, 2 is in F0, but 3, 2 is not in F1. Or you can say 3, 2 is different from everything in F1. Either way is fine. Okay, they are basically saying exactly the same thing. There we go. So, do we really want to still go through question number 4 and 5? I mean, it's okay if you guys say yes, but I'm just checking. Oh, I got... maybe not. Okay. Alright, so... Alright, so we got people asking 6 and 7, but specifically I'm asking about question 4 and 5. So it doesn't look like anyone wants to go through those. Okay, so we'll skip those two for now. So now we get to question number 6 and question number 7. So 6 and 7 are related, okay? Because question number 6. Okay, fine. We'll go through 4 and 5. Now, of course, my question is, okay, which is not something that you guys actually have to answer, is it really helping, if I go through all of these questions, versus just go through a few of them, because the technique is really kind of the same. All right, so let's go to question number 4. Question number 4 has the first part being a surjection but not an injection. So we want to use up everything in the codomain, but we don't want everything to map to unique items from the domain. So the starting point is actually pretty close. The starting point is not even a function, but it's pretty easy to turn it into a surjection by changing y0, and it is not going to be an injection. So f0 in this case, I would keep 0, 0, I would keep 1, 3, I would keep 3, 2, and you can see the only element that is not that is in the domain but not mapped to anything in the codomain is 2. So we just have to introduce 2 something in here, and we want it to be not an injection, so it has to map to one of the things that is already mapped to, which is either 0, 1, 0, 2, or 3 cannot be 1. So we can pick any one of the 3. It doesn't really matter which one, so I'm just going to pick 0. Okay. And then we have to, because we want to make this a surjection, that means we also want the codomain to only consist of items that are mapped to. So that would be 0, 2, and 3 only. Alright, so that's part 1, and then part 2 wants it to be an injection but not a surjection. Okay. So we want it to be an injection but not a surjection. So we'll keep 0, 0, 1, 3, and 3, 2 in it. And this time we want 2 to map to the remaining item in the codomain. Well, in the original codomain. So that would be 1. Yeah, so we map 2 to 1. That will make F1 a injection, but it will also make it a surjection. So to make it not a surjection, we just have to change Y1, so it has 1 extra element, 0, 1, 2, 3, and then add a 4 to it. That solves the problem. And then F2 wants to make it a bijection. So that's kind of the same thing as F1, so we'll make it exactly the same as F1. So F2 and F1 are indeed the same. And this time we leave x2 and y2 the same, because we want all 0, 1, 2, and 3 in both the domain and the codomain. And now we want to look at the intersection. So the intersection has the first 3 components. So that's the only thing we can quote. Okay, so 0, 0, 1, 3, 3, 2 is in the intersection. Okay, I'm just double checking the parentheses. The union is kind of like the intersection, except that it has 1 more item in it, which is 2, 1. And there's also a 2, 0 in it. Okay, so we'll start with this one. So I'm just gonna copy and paste, and then just add 1 more item, which is 2, 0, as a part of this. So now we want to know what is F1 minus F. So F1 minus F is, so this time we do have something in F1 minus F, because 2, 1 is the element that is in F1 but not in F. Now it is important that this answer not only have 2, 1, but also the curly braces, because the minus operation, in a set as a set operation, gives you another set. So if somebody gives me the answer of just 2, 1 in parentheses, I would have to take points off, because it really needs to be a set, not just a 2 tuple. And then we get to the last one, which is is something in F0 that is not in F1. Basically, that's what it's asking. Okay, it's basically asking, is F0 minus F1 an empty set, or not an empty set, I should say. Alright, so we look at F0. This is F0, and this is F1. And we can certainly find that 2, 0 is in F0 but not in F1. So now we say the answer to part 7 is true. 2, 0 is in F0, but 2, 0 is different from everything in F1. There we go. Finally, we are moving on to question number 5. Alright, so question number 5 is asking first what is an injection but not a surjection. And we start off with an injection, a bijection to begin with. So in this case, F0 is going to be the same as the original F. There's no need to change it. Y0 is the only thing that we need to modify, which is 0, 1, 2, 3, and then add a 4 to it. That will make it not a surjection. And then the next one asks, we want it to be a bijection. Nothing needs to be done. That's an easy one, right? No changes to F1, X1, or Y1. And then the last part, we want it to be a surjection but not an injection. Alright, so we want it to be a surjection but not an injection. So that means we have to make one of the items map to the same as somebody else, right? So now we need F2 to be changed. And doesn't really matter which one you change. Okay, so we got 0, 0, 1, 3, 2, 1, and 3, 2. Okay, so that's the one that I'm going to change, and it doesn't really matter whether you change it to 0, 1, or 3. Okay, as long as it's not 2, we'll be fine. Okay, so we'll just map 3 to 0. Okay, so that will make it not an injection, but it is also not a surjection at this point because we are not using everything in Y1. So now we have to make Y2. So we have to remove one element from Y2, so that Y2 has exactly only the elements that are mapped to, which are 0, 1, and 3 only, because 2 is not mapped to. So that answers that question. And then the intersection is going to be the first 3 items, right? Yep. Okay, so that's just going to be 0, 0, 1, 3, and 2, 1. Those 3 elements can be found in all 4 sets. The union is going to be, the union has everything, right? So you can just pick the largest one that we already have, which can be F, can be F2, and then just add the one that is missing from it. So the only one thing that is missing is from the original F, where 3 is mapped to a 2. So there we have it. F1 minus F is an empty set because we are not changing F1. Well, okay, so F1 starts off the same as F originally, but we don't have to make any changes. So that's why F1 and F are the same. And then for part 7, can we find something in F0 that is not in F1? That's basically what it's asking. So F0 does not need to change from F, and F1 does not need to change from F. So the answer is false. Every element in F0 is found in F1, and we're done. Alright, so we finished all 5 questions. Time to move on to question number 6. So question number 6, there are also multiple versions. So if yours doesn't look like this, it's perfectly normal. Okay, it's not a big deal. So the one thing you want to do with question number 6 is, well, I mean, having a calculator really helps, but you know, it's not 100% necessary, but it helps. So we'll see what to do. we want to use function k. This is how function k is defined. It's using the function g in the aleph null module. And the question specifically referred to function g as defined in the aleph null module. So, so there should be no confusion of what g is referring to, because there's only one mentioning of function g in aleph null. All right. So now we look at this, and basically, in terms of x, y, and z, 4 is the x, 9 is the y, and 5 is the z, and you have to apply the g functions in this particular nested fashion. So in case anyone wants to know how that's going to look like, it really is just plugging in x, y, and z. So one way to do it is to replicate the original, or not the original, but the equation, and then you just substitute x as 4, y as 9, and then z as 5. Okay, so the way we resolve this is, I usually just resolve the things, the one thing in the innermost portion first. So that would become 9 times 10, the whole thing divided by 2, plus what is the second one, which is the 4. Okay, and that becomes what? G of, so we got 45 plus 4, which is 49. And now we have 4 plus 49, that's 58. Okay, so we have 58 times 59, the whole thing divided by 2, plus 49. And if you have a calculator handy, this really should not be difficult to do. I mean, even if you don't have a calculator, you can probably do this by hand. I'm just popping up a calculator right now. So we got 58 times 59, the whole thing divided by 2, plus 49 to it. So we have 1,760. There we go. On to the last question. So the last question is the reverse. Okay, so the last question says we have a function k which is independent to the function k in question number 6. I specifically said right here, k is defined independent to the definition of k in other questions. So do not use the definition of k in question number 6. However, it is still true that k is mapping from n times n times n to n. It is also still true that k only involves the nested application of function g, similar to this but not necessarily the same as that, as defined in the aleph null module. So this time I give people, or in this question, I say k of 527 is 1383. So I want to reverse back and figure out, how is function k defined as a nested application of function g. So now let's go ahead and check out how to do this. Okay. So the key to do this is to apply the inverse function. That's basically the key. Okay, so we want to find out what is the inverse, what is g inversed applied to 1383. Okay, and to do this, you probably want to use a spreadsheet or a calculator. I personally would use a spreadsheet, just because once you enter equation, you're done, right? All right, so since I'm going to give you the full answer, so I'm going to go back to where the function g inversed is defined. And for those people who thought, hey, this function, may be useful, let me just put it into a spreadsheet or put it, pre-program into my calculator before the exam. Well, good for you, because that means you probably shaved a little bit of time in answering the questions. And then for those people who say, but Tech, if you knew about this, you should have told us that we could have prepared for this class, for this exam in this particular way. All I can say is I didn't know what I was about to ask. until like literally the day before the exam. So besides, how you study is you, right? I mean, that's something that's up to you to decide. All right, so I think we see some text messages going on. I will let people reset their Discord so that they can hear me again, and I can drink my coffee. All right. So I'm guessing refreshing helped. All right. All right. So now we just look at W, because everything is kind of based on W, and then we just enter this into a spreadsheet. So I don't know what spreadsheet you guys want to use. Google Sheet works really well. Okay, I personally really like to use Google Sheet, but it takes a little bit of time to set up and stuff like that. So I'm going to use LibreOffice Calc, because LibreOffice Calc is fairly easy to work with and it starts faster compared to Google Sheet. Alright, so there we go. So the first thing we want to do is to enter this equation. So given n, okay, I will even use an n here as one column, and so given n, we'll give it a particular value. In fact, we'll use the same value as what the question has, right? And where is my question? Oh, no. I think I just used the same window to... Nope. Uh-oh, where's my question? Oh. That's okay. I can open it again from the other side. There we go. Alright, so now we have the question again. All the way down here. 1383. Okay, so go back to the spreadsheet. So we have 1383 here. And now we want to find out what is W of n. So according to the notes, which we checked in class. Okay, so we did this at least once in class already. So we checked that this actually worked. So we want to take, equals, take the floor of, and then we have the square root of 8 times whatever n has, which is this thing here, plus 1, and then minus 1. Oh, okay, I need a open paren before the square root, and then close paren over here. The whole thing divided by 2, and that's what I want to take the floor of. So the floor of that is 52. So Wn is 52, and from here we can see x of y of n is n minus g of wn. Okay, so now we have y of n. So it's just really the same as this number times this number plus 1, the whole thing divided by 2. And oops, I missed one step. It is n, which is a2 minus that. There we go. So we know y of n is 5, and then x of n is w of n minus y of n. Alright, so this is x of n, and it is what again? wn. Yep, so it's w of n. Oh, I need to use the equal sign first. Equals wn minus y of n. And there we go. Alright. So what do we have at this point? So what we now know is we resolve back to the x and the y. So if we go back to the text document, so now we know this gives us the coordinate of x is 47, y is 5. 47 and 5. There we go. So now we apply this one more time. The g inverse of 47. And then we go to the spreadsheet, because this is why I like a spreadsheet, because you can just kind of copy and paste the cells with all the formula and equations, and then just change the one value that is independent, so all the dependent values would change. So I think we have to change this to what, 47? Yep. So we change this to 47, and we can see that x is 7 and then y is 2. So it gives us 7, 2 as the answer. Alright, so this gives us 7, 2 as the answer. Let me just double check. Yep, x is 7, y is 2. There we go. Alright, so now this is not the final answer, right? This is just the technique to find the answer. So the question is asking how is k defined? So what we can see at this point in the calculation is we got the 5, the 7, and the 2 back already. So the question is, how are these things nested, right? Okay, so 5 is the x, y is the 2, z is the 7. So now we know k is the outer g is dealing with the 47. So the outer g is having g of z, which is the 7, y, which is the 2. Okay. And then the leftover is the x, which is the 5. There we go. And then one more close paren. That's how k was originally defined. So that's kind of the answer of question number 7. So I'm switching back to the text channel now and see what I have been missing. You should not be getting irrational numbers because of how w is defined. Because when we define w, there's a floor function, and the floor function always returns a natural number. Well, in this case, a natural number, but in general, it always returns an integer. So I think if you follow the wn function here, you should always end up with an integer and not an irrational number. So that's my feedback to Jack's question. All right, so we have just looked at the entire answer. Are there any questions about the test? Alrighty. So if there are no questions about the test, we are going to continue with lecture material. The first thing is, let's see what the time is. It's 55. We got 25 minutes left. Let's take roll. No, once the time is announced, I cannot add more time to the exam, because some people may have other things that they have to do after the exam, and they have scheduled everything around the announced time, so I cannot add additional time. And we really don't have time, additional time either. And then the next question is, if we want to solve question 7 with pen and paper, what would be the solution to it? Use a separate calculator. I mean, how would you solve a quadratic equation, right? I mean, if you need to solve a square root, you need to solve a square root. I don't know. I mean, solve a square root however you need to do it. I mean, you can probably use a lookup table. I mean, that's how people used to do it. Actually, the square roots that we are dealing with is not too bad, right? I mean, 8 times, okay, just for the sake of argument. Just for the sake of argument, okay? Let's take a look at this again. So I'm not being argumentative, but I'm just curious of how difficult is it in this case to calculate 8 times n plus 1's square root. So n is 1383, so we'll go ahead and say, tell me what is 8 times this number and mine plus 1. Okay, so we are looking at the square root of this, right? So to find the square root of this without using the square root function, you can look at this and give it a reasonable guesstimate, right? So we can see that 100 times 100 is 10,000. Okay, so we start with 100. So we say, so we start with 100, and then we ask, what is 100? What is this number times itself, right? Nope, not plus, times. Oh, it is a times, but not itself. Times G2, there we go. So if we move this on a little bit, we can see that, okay, 105 is probably pretty close to it. So because the next one is going to go over, which is not what we want. So we know the true square root of 11065 is between 105 and 106. But since we have to take the floor, right, after doing all this stuff here, so you can basically take the floor of one part first, and there are several ways to do this, but you can say it's 105 point something minus 1, which is 104 something, divided by 2, and then the whole thing, take the floor of that. So it is still doable by hand. It's just that you have to start with a reasonable guesstimate, and then do your math kind of quickly using the squares in order to kind of find out where the solution is. You can use binary search too. I mean, there are different ways to do this, but it can be done using pen and paper. Yes, but you're not restricted to pen and paper either. So it's an interesting question to ask, but for the most part, there's no limitation placed on anyone in this class to only use pen and paper. Alrighty, so now that that is done, let me go back to the modules and we'll take row. Okay, we'll go ahead and take row and make that and it's March 1st already. Alright, so I'll give you guys till 1:30 to do this, and the date is March 1st. And go to questions. Alright, so let's pick a row. Let's make it square root. Well, just square. SQUARE. I'll also take SQR. And update question. Save and publish. There we go. The relation homework is just assigned today. Then the answer is yes, I will go over that after it's due. Alright, so the roll taking quiz is already up. It should be up. And then the magic word is square, SQUARE, or SQR, all lowercase. That is correct. Either one will work. So just let me know when you're done with the roll taking activity, then we can resume the instruction. Nice, thank you. Cool. All right. Thank you, thank you. All right, so you do have a new homework assignment that's due in a week. That has to do with relations. But before we finish relations, I think we have one last thing that we have to talk about. And that has to do with partial ordering. We explained partial ordering already. Okay, we kind of explained the smooth and rich thing. So we talked about this already. And the bottom line is, in a partial order, it is possible that there are two things in a set such that they do not relate to each other. So in this case, not smooth but rich versus not rich but smooth, those two we cannot relate. We cannot find out which one is at least as attractive as. Okay, so and that's a problem. Okay, sometimes it is a problem because if you are trying to rank game players, okay, in the game, and you say, okay, this person is the player of the week. Okay, you want only one person to be ranked on all the way on top. But if you use a method that is not totally ordered, instead it is partially ordered, then you might end up with a group of people in which there's no way to determine ordering within that group. So partial ordering is useful in some cases, but it is sometimes not what we want, and sometimes what we want is total ordering. So what is total ordering? Total ordering is almost the same as partial ordering. You can see that it needs to be reflexive. The relation needs to be reflexive. It needs to be anti-symmetric. It also needs to be transitive, which are all of the things that we need for partial ordering. But in order for a relation to be totally ordered, it also needs one last thing, which is comparable. So comparable means this quantified statement is true for R as a relation defined over X. So let's check this out and find out what it's saying. Okay, for all E, F in X. Okay, so E is a variable bound to any element in X. F is a variable bound to any element in X. For every way to pair E and F, okay, in other words, they can be the same, they can be different, but for every single way to find a pair, to fill in this pair of variables with values such that the value is an element in X, we want this expression to be true. We want ERF or FRE to be true. So what that really boils down to is EF is in R or FE is in R. So if you cannot relate EF using R, then the disjunction becomes false, and as a result, the relation is no longer considered comparable. Okay, this is also called the trichotomy law. So this is the only difference. Okay, and having this additional requirement on the relation, now we have total ordering. With total ordering, that means between any two elements, we can always find how they relate, and that is useful in the sense of we want to find the best player of this week, of a particular game. There won't be a tie. Okay. Well, I take it back. There can still be a tie, but at least we will be able to relate every player to every other player, because it is a less than or equal to kind of relationship. So we can at least tell whether two players are ranked the same or not. Whereas in the case of a partial ordering, we cannot even tell whether two players are equivalent to each other or not. They're just not related. So with this done, okay, we are done with relations. So we are done with the entire topic of relations, and the assignment is already active. You have 1 week to work on it. And I can show you what it looks like. So with this assignment, it is a single submission assignment. So unless you are sure that you are done with it, don't click the submit button. Okay, so you have until next Monday at noon to click the submit button. Alright. So the questions look kind of like this. Consider the not equal to relation over integers. Which of the following relation property applies? And so on. Okay, and then Aiden has a question. Wait, what about when R is less than and E equals to F? The less than relation is not even partially ordered. The less than relation is not partially ordered. Alright, so they're all kind of like this. Consider the equal relation when if R and S are both relations defined over X, and we know that R intersecting with S is reflexive, then what do we know for sure about R? In other words, if this is a known fact that R intersecting with S is reflexive, then regardless of how R and S are actually defined, and regardless of how X is defined, which of the following has to be true? That's what question number 3 is asking. Consider the less than relation over integers. Which one has to be true? So they're basically, all looking sort of like this. Okay, you just have to remember how we define, relations. This one can be a little bit trickier. This one relates the cardinality between R and X, and it asks you, which one is guaranteed. Okay. And then this one is once again asking about the relationship between the cardinality of R and X, knowing that R is symmetric. Okay, so with these you have to kind of be creative and imaginative. Okay, you have to create scenarios to basically challenge what you think is the answer. Okay, you have to say, can I find an example where this is not true? Okay, that's kind of how you want to approach these questions. Alrighty. So with this out of the way, we got 10 minutes left, and the next big topic is propositional logic. Yes, this assignment is a one try only, so don't turn it in, don't submit until you're ready to turn it in, because you cannot restart it. Okay. So now we're moving on to propositional logic, which is an interesting topic in many ways. Okay, it's interesting in many ways because propositional logic is not a new idea, not even close. Okay, so if you are to look it up, okay, if you were to do a Google search and find Wikipedia, you will find that this idea has been floating around for a long time. Okay, it's if you look at history, the 17th, 18th century. Okay, so we are talking about a few hundred years old already. In other words, it's not a computer specific type of topic. It's a lot of math and abstraction. Okay, but it is not specific to computer science. So now the question is, well, how is this related to us, right? To people who want to program computers, who want to develop programs, or to design software components and whatnot. So as it turns out, by itself, it doesn't quite do this, but it is it's the foundation of automated theorem proving. Okay, so look it up too. Okay, so if you want to look up, you can just go ahead and search for automated theorem proving. Okay, and you'll find lots and lots of entries for this, including in Wikipedia. Okay, automated theorem proving. And I know what some of you are thinking about. It's like, so that means a computer can help me do all the proof work in linear algebra, right? In differential equations, in all of your heavy-duty math classes. Well, there's that. Okay, there is that. Okay, and if you go to certain resources online like Wolfram Alpha and Mathematica and stuff like that, they're getting pretty close to being able to do all that already. But this is not the kind of theorem proving that I'm talking about. The theorem proving that I'm talking about is proving your program is correct. Okay? How do you know your sorting algorithm is correct? Well, turns out it can be proven. Okay? How do you know your binary search algorithm is correct? Well, turns out there's a way to prove it. So when I talk about automated theorem proving, I am talking about how do you prove an algorithm or a program is correct. And if you can do that, if you can mathematically prove an algorithm is correct, there's no need for test cases anymore. Okay, because you have just conclusively using logic, okay, to basically say if the input meets these requirements, then the output will have to meet those requirements. And if those, quote unquote, those requirements is what the output is supposed to be, then your program is going to work correctly, assuming the input meets the requirement for the inputs. And Jackie is saying this is sort of like vector spaces from linear algebra, making your own operator and that stuff. It's actually a lot simpler. In many ways, it is simpler compared to your linear algebra class, because trust me, all of these, they're all based on Boolean operations. Okay, and we have used Boolean operations already in this class a lot, and in programming in general as well. So automated theorem proving is useful. And why is it useful? So you want to look into, let me see whether it has explanations or not. Okay. Ultimately, it has to do with computer security. Okay, so you want to look up computer security automated theorem proving. And there are many articles, many links that talk about this. Because if you can, okay, so to understand what the problem is, we can point to certain incidents. One is called a heartbleed exploit. So if you just go to the heartbleed bug website, there's an explanation of what this is, and it's basically it basically boils down to incorrect coding, so that the program not by design but because it is not well written, it would end up having a security risk exposure, and but it can be stopped. Okay, in other words, if we can use automated theorem proving to show that a piece of code is doing only what it is supposed to do and nothing else, then this would not have happened. So this is what people are trying to do now with at least the very core components of operating systems, the networking stack and whatnot, things that are very, very central to cybersecurity, is we want to have a conclusive proof that this piece of code is going to do only what it is supposed to do, and then we define what the input may look like. Okay, we have to specify this is what the input may look like. So this topic, okay, this entire topic has a lot of relevancy to computer security, and we know that cybersecurity is not going to be it's not a fad. Okay, it's not going to go away. It will only become more and more and more important. Automated theorem proving used to be an AI topic, an artificial intelligence, topic. I would say back in maybe the 80s, okay, that was a big thing. Okay, it was a big thing to try to use computers to prove theorems. Back in those days, computers were not nearly as powerful as what we have now. Neither do we have the storage and stuff like that. So before long, computer basically ran out of steam, and it was a great idea, but because the machines had limitations, and as a result, as a field, it basically quote unquote died, or it went into hibernation. And also back in those days, the internet was not even a big thing. Okay, that's when Bill Gates, said, "Hey, we don't care about the internet. The internet is not going to be a big thing." Guess what? It did become a big thing, right? So back in those days, there was not really that much of a cybersecurity spin to this whole thing. It was more of an academic pursuit, at the time, and the U.S. and Japan were basically competing with supercomputers and see who can get to it first. And of course, neither did, because even those computers, mainframe computers, didn't quite have the processing power necessary. But these days, it's different because we do have cybersecurity, as a main issue that we have to deal with. And then on top of that, we also have plenty of processing power. So what we did not have before, which is, one, processing power, resources that are needed to do this, and two, rationale to do this, both are present now. So that's why there are people doing research on automated theorem proving, but applying that to prove that programs, or at least some components inside an operating system, is 100% correct. Okay, we are not throwing test cases at it. We are mathematically proving that it does work 100%. So that is why this topic is kind of interesting. I mean, the curriculum of 440 probably has not changed since the 80s. Okay, so back in the 80s, this is more of a curiosity. Okay, it is more like a lot of computer science professors were math professors transitioning into computer science professors. So they talk about this from the math perspective. Like, this is important concepts in math, and I was a mathematician before I became a computer scientist, and therefore, I'm teaching this. So that was back in the 80s, possibly in the early 90s too. But now, I see practical applications of what this can be used in industry. So I think this is kind of an interesting perspective. So now that we know some of the reasons why we want to study this, the next question is, I'm just looking at the time right now. We got about 10 seconds, so I'm not going to go too deep into this. But I do want you guys to read ahead of me before Wednesday's class. So try to finish this entire module. I know it is long, and I know it is parts of this can be difficult to understand, but just try to see if you can connect the big pieces. Okay, instead of focusing on the details, try to focus on the big pieces and see how the big pieces connect with each other. And then on Wednesday, I'm going to go over the details. Okay, I'm going to go over the notations, the details, and some of the definitions. That's what we'll do on Wednesday. And if you have started on your homework, before Wednesday, if you have, so don't post your question in, like a screenshot, but you can always ask, what makes a relation blah, right? What makes it, asymmetric, and so on. And you can use examples, but don't use examples in the test. Okay, in your homework assignment, you can always just kind of come up with your own examples and go like, okay, what about this one? Okay, how do we know whether this one is symmetric or not? But I want you to kind of spend the time to think about that before you ask those questions. In other words, you should be fairly sure what the answer is supposed to be, but you're not 100% sure, and that's the reason why you're asking. All right, so we are Done for today's lecture. Not quite as far as I originally planned, but that's okay, not a problem. But the next big topic we're getting into on Wednesday is propositional logic. And it has all of these topics, and it is a long module. This is way longer compared to relations. So you do want to kind of plan ahead of time, spend the time to read before class, because if you don't do that, it's gonna be a difficult module to get through. All right. So are there any questions before I stop streaming for today? Oh, okay. I see some people are popping out already. I guess there are no questions then. Alrighty. If there are no questions, I'm gonna stop the streaming. I'll still be on, Discord for a little bit, just in case some people have questions, and then I'll be off maybe by 1:30 or so. Have a nice day, and I'll see you guys on Wednesday.